Okay. So for the last talk of this session on measurement induced physics, we have Sarah Murciano who will tell us about measurement altered criticality.
Yes. So welcome to everybody, and thanks the organizer for the opportunity of presenting, let's say, a series of ongoing work together with my collaborators at Caltech. So you and Stephen are PhD students there, working with Jason at Lyceum, Pablo is a postdoc, and Roger is at Pittsburgh University. So I don't think I have to motivate once again why it's interesting to study measurements now, not only from a more traditional perspective, like to learn more, something more about the system, but also, let's say, to see measurement as playing an active role in order to probe novel quantum phenomena like the entanglement transitions that we have already heard in the previous talks, which have been studied a lot, both analytically and, let's say, experimentally. For instance, this is a work done in the group by MIMIC, where this entanglement phase transition could be observed. However, in this talk, I will try to focus on measurement-induced phenomena, which are more related on the to the ground state physics. So there will not be dynamics. Before explaining this theory of measurement altered criticality, I would like to mention another setup where a static setup where measurements also play a crucial role, and this is related to what happens in the measurement-based quantum computation. For instance, the possibility of using measurements and feedback in order to prepare non-trivial states, like, for instance, a GHZ state. Like in this picture, what I show is basically what happens when we start from the simple product state in the X basis, and then turn it into a cluster state, which is an example of a resource state, that can be used by doing measurements and feedback in order to prepare a GHZ state. So this is another nice application that through which one can go from a state which is short range correlated to a state which is long range correlated. And another setup in which measurements play a crucial role is the quantum teleportation problem, where basically Alice can send a wave function to Bob, and the key ingredients that enter into the game are entanglement, measurements, and classical communication. Measurements play a crucial role here, and I will come back to this at the end of my talk. But what I want to focus on today is basically the effects that measurements can have on the ground state of critical systems. Why critical systems? Because they are characterized by, for instance, a logarithmic one-dimensional systems, and in this case, critical systems are characterized by a logarithmic growth of the entanglement, power law decay of correlation function. So one could expect that even more nuanced modification of the both entanglement and correlations can arise in this kind of settings due to measurements. And let me say that the pioneering work about this subject has been done in the group by Ehud Altman in a work published last year. Where basically they studied this measurement altered criticality on the Luttinger liquid. Okay, so what do I mean by measurement altered criticality, and how can we realize it? I will focus on the ground state of the Ising spin chain. So just to set the notation, this is the Hamiltonian that can you use this? Yeah. This is the Hamiltonian that I will focus on. So I put the transverse field along the x direction, and by varying the transverse magnetic field, one can go from the ferromagnetic to the paramagnetic phase, passing through the critical point, which is the one where we will initialize our system. Now, at this point, if I would just do projective measurements on this critical system, I would turn this wave function into product state. So I want to do something less trivial, and in particular, I want to I want to implement a weak measurement on this system. How can I do this? I can consider some additional degrees of freedom that you can think of, and you can think of them as the ground state of the chain, but now tuned in the paramagnetic regime. So when H is larger than J. And this is the first step of the protocol. Then at this point, since my idea is basically to perform measurements on these ancillary degrees of freedom and check the effect that we have on the system. So I need some entanglement between the system and the ancillary. And indeed, the second step consists of weakly entangling the critical spins with the ancillary degrees of freedom. So I will apply some unitaries that do this game. And in particular, I can focus on two classes of unitaries. This one, which involves Z on the ancillary degrees of freedom and X on the system, meaning that this unitary will preserve the Z2 symmetry of the system because it involves X. Or I can choose a unitary that involves, again, Z on the ancillary degrees of freedom and, for instance, Z minus 1 on the system. And this will break the Z2 symmetry of the system. Now, at this point, I can perform my projective measurement. And in particular, one can measure these ancillary degrees of freedom in the X basis, such that the projector non-trivially commutes with the unitary operator. And this is the post-measurement wave function that we get. So this basically denotes the projector into a given measurement outcome, A tilde. This is the state that I get once I entangle the critical system with the ancilla. And this is a normalization factor that they have to apply in order to normalize my wave factor. And this is related to the probability of finding A tilde as a measurement of the output. Okay, if I massage a bit this non-unitary operator that I get, I can rewrite it as a non-unitary operator acting on the original critical system. And here I post-select for a given measurement outcome. For instance, the uniform one. Or that in this case is also the most likely. And I want to study the effect that this non-unitary operator, which is basically what encodes my weak measurement, has on the critical ground state of the Ising spin chain, both at the level of the entanglement and of correlation function. So how can I do this? How can I study the effect of this weak measurement? And the strategy that I will use is the following. So in general, if I want to study a correlation function of a given observable, A way to do it is by considering the corresponding path integral formulation of the problem that one can write in terms of the right and left Majorana fermions. And so basically, if I show it in the x tau space-time, where x is the spatial coordinate and tau is the basically what I should do is I consider an imaginary time evolution from -∞ to 0, corresponding to the preparation of this ground state of the Ising spin chain. Then I will insert my observable at time equals 0, and then the imaginary time evolution from 0 to +∞ corresponds to preparing the graph. Now, once I insert also this non-unitary operator M, basically what happens is that when I evolve until time tau equals 0, I have to insert not only this observable A, but also this non-unitary operator that now will act at all spatial point because of the way in which it's defined. No? It's a sum over J, it's a sum over all the lattice sites. So at the end of the day, the correction coming from the weak measurement just corresponds to a defect line that acts exactly at tau equals 0. And the question is to understand how this defect line affects the original critical action of my theory. Okay, so let's see how this happens for the two unitaries that I was mentioning before. So we start from this unitary that involves X on the system and Z on the unstated degrees of freedom. And if we compute the corresponding post-measurement wave function, it will involve sum over j xj. So again, of course, this also respects the Z2 symmetry of the system. And if we want to write down the corresponding defect line, basically this we have to understand how to write it, this operator in terms of the corresponding macroscopic operators of our theory. So, for instance, what we can do for eating is using the dictionary between the lattice operators and the macroscopic operators. And we see in the dictionary that X corresponds to the epsilon field, which is one of the three primary fields of the Ising conformal field theory, together with the identity and the spin field. And this has scaling dimension equal to 1. So basically, this defect line is a marginal perturbation that we are adding to our critical theory. And the question that we want to address is now how this marginal impurity action affects the original properties of the theory. And as I said, I want to check the behavior of this impurity action, both at the level of the entanglement and the correlation function. So at the level of the entanglement, as we already heard, for the ground set of critical systems, the entanglement grows logarithmically as a function of the subsystem size. And every factor is related to the universal properties of the underlying macroscopic theory, which is the central charge, that is equal to 1/2 for Ising. Now, if we perform our measurement protocol, it turns out that we still preserve the logarithmic growth of the entanglement, but with a different prefactor that now non-trivially depends on the measurement strength. So basically, the effect of this measurement alter criticality is to preserve the logarithmic growth of the entanglement, but altering the prefactor of the logarithmic term. And similarly, if we compute the behavior of the two-point correlation function of these Pauli spin operators, we can see that the pristine power law decay continuously change as a function of the measurement strength. So for all of them, except for X, where basically the correction comes as an overall prefactor of the correlation function. Indeed, if we rescale all the lines, we can see that they collapse. And these computations can be done exactly because let me mention that this operator preserves the Gaussianity of the ground state of the Ising spin chain. So one can compute exactly both entanglement and the two-point correlation function. Okay, so now let's change the unitary operator that entangles the system with the ancillary degrees of freedom. And for instance, we can choose a unitary operator that now breaks the Z2 symmetry. So as we would expect, once we break this Z2 symmetry, also the non-unitary operator will have this feature. And indeed here Z appears, which is odd under Z2. And in order to understand the effect of this non-unitary operator, what we have to do is using again the dictionary between these spin operators and the corresponding fields in the continuum limit. So in this case, V will correspond to sigma, which is a primary operator with scaling dimension equal to 1/8, meaning that now our defect line is relevant, so not marginal as before. It becomes different. And so now the question is once again, how this relevant impurity action alters the original critical properties of the theory. the level of the entanglement, now we have a very dramatic change, because the logarithmic, we lose this logarithmic growth of the entanglement, and the effect of this relevant perturbation is somehow like cutting the system into two parts. And so the behavior of the entanglement simply goes from a logarithmic growth to an area law behavior. So we can say that the effective central charge, just meaning the prefactor of the logarithmic term of the entanglement, is zero, because we don't have a logarithmic growth. On the other hand, if we compute the two-point correlation function, we see that all of them change in a very dramatic way, because the power law decay becomes -4 for all of them. So the signature of the measurement after criticality is much more stronger with respect to the case that we saw before. Because on one side, the behavior of the entanglement is completely changing. We go from a logarithmic growth to an area law behavior. And at the level of correlation function, we still preserve a power law behavior, but the power law exponents are very different. Okay, so we have seen what is the impact of this measurement alter criticality for the ground state of the Ising spin chain. Now, in all this story, from the beginning, I was saying that I was choosing the most.
Before you move, the fact that you can have area law with power laws is because the exponents are large enough, or?
So if you go to the projective limit of this theory, you can write down the parent Hamiltonian of the theory, and you can think of this state as the ground state of an Ising spin chain with a long-range interaction. And the long-range interaction is as power law decay equal to 4. So if you have this kind of ground state, I think also Lucas works on this, where you can find area law behavior of the entanglement on one side, because this power law decay is very fast, it's 4, and correlation function, power law decay and correlation function. Okay, so I was all these results somehow were relying on the fact that I was choosing a specific measurement outcome. Now I was post-selecting for a given measurement outcome, and we have already heard that this, of course, gives some problems, because in principle the probability for picking up exactly this measurement outcome in general exponentially decays with the system size. So is there a way to increase this post-selection probability? And this is a very important question that we can try to ask if we want to have an experimental prospect for measurement after criticality. So the reason for which we choose to study the effect of measurements on the universality class of Ising is because a different microscopic realization of this model can be realized by using Rydberg atom arrays. So this is the Hamiltonian that defines my problem, these Rydberg atom arrays, which can be written in terms of this hardcore boson, Bj and Bj dagger, and the occupation number Nj. And this is the phase diagram, which has been studied in this work of this Hamiltonian. And we see that there is a line of points where basically we have a second order phase transition between the disorder and the order phase of the model. And the corresponding universality class along this line is the same as the Ising one. And let me say a few words about this phase diagram. So in this disorder phase, basically what happens is that we have a negative value of this detuning parameter delta and some repulsive interaction in this parameter V2, which basically favors the state in which the occupation number is 0. While if we go in this phase, this Z2 order phase, we get this charge density wave, which is favored by a positive value of the detuning and some repulsive interaction. And in all this problem, something important, we set V1 equal to infinity, meaning that all the configurations in which two consecutive sites are occupied are energetically suppressed. And this is called the Rydberg blockade regime. Okay, so the idea is to find a protocol to observe this measurement after criticality, where the post-selection probability is not very, very low. And the first thing that we tried to implement was to measure two consecutive sites directly on our Rydberg model tuned at its critical point. And what we observed is that if we just measure these consecutive sites, basically the macroscopic effect that we have is similar to the one of the marginal perturbation, but the post-selection probability are still very low, are between 10 to the -4 and 10 to the -8 for order 100 atoms. And these numbers basically change according to the density of sites that we are measuring. So for instance, if we measure two sites and then we post-select for 0, 0, and then we leave these two unmeasured, or we leave 4 unmeasured, and so on. So this is basically why these post-selection probabilities change. So the possibility of observing these a marginal measurement after criticality is still very low. On the other hand, the situation really improves if we design a protocol where we measure any other site and we post-select for the 0 measurement outcome. And indeed, if we look at the behavior of the, if we look at the post-selection probability, this becomes order 10% for order 100 atoms. And this power law exponent is equal to -4 because it corresponds to the order parameter correlation function in the presence of a relevant perturbation. So we think that this setup might have let's say, is more amenable for a possible experimental realization of the problem. Now, we don't have yet a clear understanding of why this post-selection probability becomes so large. We think it might be related to the fact that we are working in a constrained hyperspace, because, for instance, if rather than choosing post-selecting for the measurement outcome where I have 0, 0, 0, I choose the state with 1, 1, 1, then the probability of this measurement outcome is very, very low, because due to the Rydberg constraint, there is only one configuration in which this happens, which is the one in which here we have 1 and here we have 0, here we have 1 and here we have 0. So maybe the fact that we are selecting for the 0 measurement outcome in the presence of this constraint may be what is helping us in having such a large post-selection probability. Okay, so we have seen what is this theory of measurement after criticality for the ground state of Ising spin chain at its critical point. I've tried to convince you that post-selecting is not such a bad choice, especially for this relevant perturbation. Now, just as a future outlook, I want to briefly mention what can be some possible quantum science application. And one of these is the possibility of leveraging on the theory of the measurement after criticality in order to study the quantum teleportation problem, and especially the effect that imperfections might have in this kind of setting. And this is something that we have already started doing, at least for critical systems. And one nice application of this is that if, for instance, Alice has the possibility of preparing the ground state of a critical system, because she has some special hardware that is able to do it, a possible nice application would be to teleport this critical state to several distant parties, so this Bob, by exploiting quantum networks. And so in this way, we could, let's say, have several copies of critical systems by just paying the fee once, because Alice has to prepare it. And once we have all these critical systems, we can ask, okay, what can be some possible application of these? And I think that an application of both critical and measurement alter critical systems might be quantum metrology. And this is something that is already quite well understood, that critical systems and in general entangled states can be used to beat the standard quantum limit. But the specific measurements that allows us to observe this metrological gain and the robustness of these states in this kind of setup is still something that I think should be better understood. And yes, with this it's thanks.
Time, so we have time for questions. I see already, Jamil.
So thank you so much. About the marginal case, you said that the conformal charge changes with the strength of measurements continuously.
The prefactor, it's not really the central charge that changes, it's just the prefactor of the logarithmic term.
Very good. Okay.
But maybe a related question. So, but in your field theory construction, is there a way to see actually what would be the central charge?
I don't think there is a change of criticality. It's just really the prefactor of the entanglement entropy that changes.
But if you look at the definition of central charge from the, let's say, Casimir or whatever,
yeah, no,
you will not.
Only for let's say the most CFT connection thing that I can say is more in the relevant case, where I think one would flow to some kind of boundary conformality theory because of this relevant perturbation, which also breaks it into symmetry, but not to the level of
So Pedro, and then
so you took a critical state for your initial state, but you could take a state with volume. Say, is there some you had these two possibilities of doing measurements? Could you pass from a volume law to area law because of these measurements right away? I mean, that in critical state that you could also go to the area law.
So suppose that I have the possibility of write down my defect line action for this particular state with the volume law entanglement. I think that the effect of a relevant perturbation is always to kill completely the entanglement. I don't think that you could find something between. I mean, unless the measurement strength is not very large, but if we are in the thermodynamic limit and we don't have size constraint, I think that you would go to area law behavior.
there was another question. Yeah, look.
It was related to your comment. You say you go to the boundary conformity theory, but don't you get then a real product state? So isn't it?
It's like when you compute the two-point correlation function for easing, in a BCFT. And if you are far in the bulk, then you just find that the power is -1.
Here you're exactly on the bulk, right?
But I have to compute close to the boundary, and if you are close to the boundary, but always, let's say, an epsilon far from the boundary, such that I don't see any short physics regime, then the two-point correlation function becomes -4.
Yes.
It's like called extraordinary transition.
But the entanglement is exactly 0 at that limit, or not?
In the limit in which the measurement becomes exactly projective, yes, but here the measurement strength is always.
Was it you? Okay, sorry. Yes, go ahead.
Thank you very much. The Liebman Hamiltonian can be seen as a transverse easy model class longitudinal.
In the antiferromagnetic regime, and this is why also we have this line of. Like for easing, for the ferromagnetic easing, we only have one critical point. Now, while here we have a line of points, and yes, you can rewrite them in spin variables. like in this you have relate as X, and then and J you can relate to Z. Yeah, and in this case, the analogous of the because you have this longitudinal field, you don't have anymore this Z2 symmetry that I was mentioning, and now the analogous of this Z2 symmetry will be the translation by one side. It's the only symmetry that remains in your theory.
Very good. Okay, maybe the last question from Sal.
Can you say that the measurement is strong or weak depending on what you choose to post-select in the Rydberg part? Because like depending on, I mean, I just said if you select on 111, it's very rare to see. Can you also say that it's like weak or stronger choice?
No, I don't think that it's. It might be that also that the choice of the measurement outcome tells you whether the what is the corresponding operator, because like how can I say that it's exactly sigma or exactly epsilon? I can use again the dictionary between this and J and epsilon or sigma. And by exploiting this dictionary, I can find out what is the corresponding operator that I find. So maybe, yes, this you can, the measurement outcome can tell you whether the measurement is marginal, relevant or not. But in the specific case that I was saying with 111, this would be also give an epsilon perturbation just with, just with very, very, very low selection probability. But yes, in general, I think you can relate the measurement outcome to the operator exactly because of this translational symmetry that you have in the game. So whether you respect it or not, you can find a field in the defect line that is odd or even under translational symmetry. I don't know.
Very good. I think this is a good point to transition to a coffee break. Let's and I would say to try to be on time, we reconvene at 5.